Hello, and thank you for joining us again. I am Jasmine Navarez, Digital Content Coordinator here at Simulations Plus. I'll be hosting today's webinar behind the scenes, making sure we don't have any technical difficulties. In this webinar, David Miller, Vice President of Cheminformatics, and Rafal Bashor's Principal Scientist, will give you a sneak peek of the latest version of our flagship machine learning platform for ADMET modeling and discuss its extended capabilities. Our Senior Director of Business Development, Eric Jamois, will serve as our moderator today. A few housekeeping items before we begin. We take your privacy rights seriously by registering for and attending this event or participating in the Q&A session. You are allowing us to contact you for follow-up. You may ask questions via the questions panel on your dashboard at any time. If you need assistance, please use the hand raise icon. We'll address all questions in the Q&A after the presentation. This webinar is being recorded for playback for those that can't attend live due to unmanageable time differences. Before we begin, I'd like to conduct a short poll to better understand your familiarity with ADMET Predictor. And I'll go ahead and launch that now. And I'll give everybody a couple seconds to answer this first question. And it's, which aspect of ADMET Predictor are you most interested in?
Your models. HTPK, yeah. All right.
A couple more seconds here. And I'll go ahead and end it there. And I'm happy to say that most are interested in the new models and enhancements. So I'll pass it off to Eric.
All right. Well, thank you, Jasmine, for this kind introduction. Yeah, it looks like our users are primarily interested in the very thing we're going to be presenting on. So that's great. So, well, thank you to all of you for joining us in this special event. And it's my pleasure to introduce our VP of ADMET Cheminformatics, Dr. David Miller. And so I think David is going to take us through the highlight of the new functionality and enhancements in ADMET Predictor 12. David, the floor is yours.
Thank you, Eric. Thank you, everyone, for attending. So today we're going to talk about the new functionality in the just released version 12 of ADMET Predictor. I think we were able to upload the installers this morning to the ShareFile website. So hopefully somebody within your organization has gotten an email about that. We don't often release the Windows and Linux version on the exact same day. Usually takes a little bit for the Linux version to come out, but this time I'm happy to say we got the Linux version out on the same day. So please look for that email. We would encourage you to download it and install it as soon as you can. Okay, let me see if the slides are working. Okay. So I am going to give a brief overview of the ADMET Predictor platform and highlight two existing features that are particularly relevant to this release. One being pKa prediction, and the other our so-called AIDD de novo design module. Then I'll outline the most important new features in this version 12 release before handing things over to my colleague Rafal for the hands-on software demonstration. I hope you'll forgive me, but I think just in the interest of saving some bandwidth, I'm going to stop my camera here and just focus on the slides. Okay, so the most important ADMET Predictor functionality is, of course, property prediction. As of this release, we offer just shy of 200 predicted properties in the categories shown here. So physicochemical, transporters, metabolism, toxicity, and what we call risks. These encompass a number of ADMET liabilities as a single number, kind of like a Lipinski's rule of 5. There is the high throughput pharmacokinetic simulation module that we call HTPK. We think of it as kind of the mini Gastro Plus inside of ADMET Predictor. It allows you to estimate a number of important PK parameters, generate concentration versus time profiles, or estimate the dose required to achieve a certain plasma concentration. ADMET Predictor includes a model building engine called ADMET Modeler. It's the engine that we use internally to build the commercial models in ADMET Predictor, and clients can use it to build their own models. It includes our proprietary molecular and atomic descriptors. It supports both regression and classification. It comes with uncertainty estimates for the regression type models, confidence estimates for the classification models, and has a nice feature that we call delta models that essentially allows clients to extend our commercial models into their own chemistry space using their own data. And then finally, there are a number of cheminformatics features. I just briefly mentioned AIDD for compound design, a 3D virtual screening functionality based on shape and pharmacophores. I'll talk about both of these in the upcoming slides. And then some more classical cheminformatics features like clustering and so on. I'll talk later a bit about deployment, so I wanted to show this slide up front. We offer the immersive desktop version with charts and other graphics. This is platform specific, so it runs only on Windows. We offer KNIME and pipeline pilot components. The command line version of ADMET Predictor has just about all of the functionality that the desktop version has, and it does run on Linux as well as Windows. And then I think maybe 2 years ago, we introduced the REST API to further simplify the importing of predicted properties and PK simulation results into other software, either third-party purchase software or in-house software. I just want to say a few things about the Linux release because we are getting more and more questions about this. So our official support is for the Ubuntu and Red Hat versions of Linux, but we do support their variants as well, things like CentOS. The software will run on Ubuntu versions 18 through 24 and Red Hat versions 7 through 9. We do distribute platform-specific binaries on Linux. So if you look in the install folder, you'll see a number of different binaries, and some of them will have extensions like this. So it's best to use the one that most closely matches your platform. We also provide both statically and dynamically linked binaries. So the difference there is that the static versions include all dependencies. So that should prevent you from having to install anything. But the static versions may exhibit incompatibility issues. So we recommend using the dynamic version if you cannot get it to run, or if you're unable to, if you're, it won't run and you cannot update the system to install dependencies, then try the static version. The static versions are denoted by the _static suffix on the binary names. And then if you're using the REST API, that supports 2 different OpenSSL versions, the 1.1.1 series and the 3.0 series. This is, again, just to make it a little easier to avoid having to install dependencies. So it's going to be tough to get version 1.1.1 on a newer system and tougher to get 3.0 on an older system. And so the 3.0 version is going to be denoted by this suffix here, and that's on the ADMET Predictor service. Okay. I mentioned wanting to highlight a couple of existing features. So the first is pKa prediction. So it's just about 1 year ago that we released ADMET Predictor version 11, where we announced a significant improvement to our pKa model. And that was through a collaboration with 3 groups where we received more than 25,000 pKa values. And that brought the total size of our training set to more than 70,000 pKa values. Since the time of the AP11 release, that work has been published. I just want to give a shout out to my colleague, Robert Franskevich from Simulations Plus. He's the one who is responsible for building the pKa model. We can now announce who those 3 groups were. So they were Roche, Genentech, and Bayer Crop Science. Even prior to that collaboration for AP11, we had a very top-performing pKa model. So this is showing results of the sample 6 pKa challenge in the 2017-18 timeframe, where our model was ranked second to a full quantum chemical calculation only, so a pretty slow method. Since the AP11 release, this is hot off the presses, but we submitted the pKa model to what was called the euroSAMPL pKa prediction challenge. That's just this year. And these are the results. So we were the top ranked pKa prediction model. I believe there's going to be a publication here, but you can use this link to see the results that have been posted. I mentioned Robert Franskevich. He has a talk on this collaboration at the upcoming ACS meeting as well. And then related to pKa, so there are a number of kind of ancillary features in ADMET Predictor related to pKa. And one of them is the pKa microstates display, where for an individual compound, you can visualize the ionization microstates, macrostates, and their populations as a function of pH. I'm going to come back to this chart in a few slides. The same colleague, Robert, recently posted a nice video on YouTube that illustrates the use of this display in a drug discovery setting. Okay, and then just briefly on the AIDD technology. So I'm going to talk about some improvements to AIDD. So I want to just give a little background on what it is. So the main idea here is to take a starting structure and generate analogs with improved properties. So how that works internally for that starting compound, we generate new virtual compounds using an internal database of intelligent transform rules. It's a file we distribute. Users can modify that and add new rules, for example. Given the resulting virtual population of compounds, we evaluate a set of objectives that the user chooses at the outset. And those can include our ADMET property models, the HTPK endpoints, 3D similarity to one or more reference structures like X-ray crystal structures, user activity models, or even external applications. So there's a call-out function where you can invoke an R script or a docking program or what have you. Then given that population and the objectives, we prune the population by retaining only those compounds that are Pareto optimal. Then those surviving compounds go back to this stage and we begin this loop again of generating new compounds, evaluating objectives, and pruning until after so many generations, you have a population that is simultaneously optimized against those objectives. And then just to highlight kind of two opposing use cases of AIDD. One you might call property optimization. So here, you're wanting to make only small changes to the overall chemistry. So perhaps you have a compound that has good activity, but has one or more ADMET or PK liabilities that you want to overcome. So here you are probably using a very precise chemical scaffold, which is a Marcouche structure that all virtual analogs have to contain. So if you know, for example, that certain regions of the compound are important for activity, you can anchor those down and allow changes only at other positions. And here's an example of a very simple analog that nonetheless has a predicted PK endpoint that's much improved versus the original. And then another kind of diametrically opposed case would be scaffold hopping, where you're interested in exploring a broader chemistry space. Here, you probably wouldn't use a scaffold, but AIDD offers another type of constraint, which is the 3D similarity constraint. So in this example, here's the starting structure. I've used a 3D model of this compound as the 3D reference structure or the constraint. And then here's an example of an analog that AIDD finds. So the chemistry is somewhat different, but you can see from the overlay here that it has a similar 3D shape and the overlay of the pharmacophore features. Okay, I'm going to come back to both pKa and AIDD as we get into the new features. Okay, so that was the overview, and now I'll outline some of the more important new features in this version. I'm not going to have time to cover absolutely everything, so please consult the README file that we distribute for a list of everything that has changed, and then of course the user manual as well. Okay, so the bulk of the last calendar year has been spent on new and improved models. We do listen to our customers, and I think over the last several years, they've indicated that improved models in particular are the most important item for them. I'll cover the new models first. So there are 4. The first is a CYP1A2 induction model, which for the time being is a classification type model. It's going to be an ongoing effort for us to expand this to include new enzymes and hopefully get some quantitative models as well. So we're just starting this effort, and this is the first model that we're releasing in this category. We have a fraction unbound to hepatocytes model that complements our FU-MYC model. And I'll talk a little more about this as we get into the HTPK changes. Low efflux MDCK permeability. We had a classification model here, but we were able to acquire new data and change that to a regression model. So it's a much better model than what we had in the previous version. And then finally, a Pampa permeability model. That is also a classification model. Most of the time over the last year has been spent on improving existing models, particularly those relevant to the HTPK simulations. So there's just been a tremendous amount of work in gathering data, fixing errors, and then rebuilding models. So I'll just go through the list here. So liver microsome clearance, hepatocyte clearance, fraction unbound in plasma, and ratio of blood to plasma. For those, we've improved the models for all 3 virtual species that HTPK supports, so human, rat, and mouse. So that's 12 models in total that we were able to improve. And then in addition to those, fraction unbound to microsomes, and 2 of the biorelevant solubility models, FASIF and FESIF. Of course, all of the details about how the models have changed, all that is covered in the user manual. I'll just kind of summarize it by saying that in almost all cases, the model performance improved. And so I'm talking about the external test set performance. A couple of cases, the performance was about the same as in AP11. But in all cases, there was a significant expansion of the chemical space, the chemical coverage. So the applicability domain of all the models should be improved greatly. Okay, ADMET Predictor 12 is including a new module that we call the DILIsym inputs module. So this estimates properties that are used to derive inputs to our DILIsym QST liver safety software. The module includes 11 models, 9 of which are new, and they cover mitochondrial dysfunction, reactive oxygen species toxicity, and then the inhibition of 3 separate transporters, MRP3, MDR3, and BSEP. This does require a separate license entitlement. The 2 BSEP models that we had previously will continue to be accessible with the transporters license. And then just a couple of announcements from our QST team. The qualification of the ability to rank order compounds by liver safety risk has been performed with this module on 2 different compound sets that are listed here. And the DILIsym development team will be releasing a full training package to demonstrate the translation process from the AP outputs to the DILIsym inputs, including the details of how this qualification was performed. So we look forward to that. Okay, so we've made a number of enhancements to the HTPK module. The first I'll talk about is the introduction of IR solution as a new dosage route. So this is what the user interface looks like now. So previously it was just immediate release tablet and IV bolus. And this just shows a comparison predicting fraction bioavailable in ADMET Predictor 12 versus GastroPlus 9.9. So these are randomly selected compounds, but from a pool of compounds that exhibited the largest differences between tablet and solution dosing as far as estimating fraction bioavailable. And the differences were very significant in the tens of percentage points. And so this is just showing that, you know, for those compounds, we're able to very closely reproduce the results of GastroPlus. Okay, so this is a feature we've been asked about many times over the last few years. Some other HTPK enhancements, 14 different partition coefficients, tissue partition coefficients are now returned as simulation outputs. So these are calculated just as they are in the GastroPlus software. Some of the tissue types are shown here. Similarly, lipid adjusted FUP is now returned as a simulation output. That's a species-specific value. You'll know that adjusted FUP has been an option in HTPK going back, I think, several releases. You just weren't able to visualize that adjusted FUP. So now you can. I mentioned the new FU-HEP model. So that is now available for hepatocyte clearance correction in HTPK. Previously, we were using the Austin correction, and that will still be available, although you will have to make a change to the underlying parameter file, the so-called HIA file, in order to do that. And then 3 smaller changes that were requested by some of our clients. CP time curves can be displayed as either total or free concentration. It was just total before. Command line runs can now specify a subset of species to run. So there are 2 different command line modes, one for running a single simulation and one for running the dose optimization. For both of those now, they both recognize this dash species argument where you can specify 1 or more species to run instead of having to run them all. And then finally, if you're inputting a systemic clearance, as opposed to a liver microsome or hepatocyte clearance, it supports multiple different units. Previously, it was just liters, hours, kilograms, and now we support these as well. Okay, moving on to AIDD. The objectives now can be assigned individual importance weights. This is something we've been asked about over the last year, especially. This is how it looks in the interface where you've chosen here. There are 3 objectives. Now you can assign differing weights to those. So if one is more important than the other, you give it a higher weight. If you supply these weights, that triggers the use of what's called multi-criteria decision analysis, or MCDA, instead of the Pareto optimization that I mentioned in a previous slide. I won't go over this for this talk, but the user manual includes a nice write-up of how the MCDA algorithm works. Tissue selectivities are available as objectives. These are based on the tissue KP values that I just mentioned. These are returned from HTPK simulations. This is how it looks in the user interface. So you have 14 different objectives that can be chosen. So this would be for the case that you want to, specifically target 1 or more tissues for the virtual compounds. I mentioned 3D similarity to 1 or more reference structures. So that's now a so-called primary objective. So it's available from the main list of objectives. It's in this interface and it's shown here. Previously, it was a bit cumbersome to use this. You needed a separate parameter file. So we've streamlined that. And then finally, we've expanded the database of molecular transforms. We've added some and we've made others a bit more intelligent. The REST API now includes the ability to generate these pKa microstate images that I showed on the earlier slide, as well as the data that is behind those charts, where you can see the population of either microstates or macrostates as a function of pH. So all 6 charts that you can see in the graphical desktop version of Predictor are now supported. That's not just from the REST API, but also from the command line. This is a feature we've been asked about multiple times over the last years. I'm just going to gloss over this, but we are releasing a new application called AP Service Test Client to facilitate both testing of the API and integration into whatever cheminformatics platform you have. There's very detailed instructions of how to use this in the manual for the API. This is the name of the manual. It's part of the ADMET Predictor distribution. But using this tool can not only test the API, but also give you a sort of picture of what calls you need to make to retrieve, let's say, certain result files from the server. It lists all the relevant requests and responses that are used to not just submit the request for properties, but also to get any sort of ancillary files that are generated on the server, like this new pKa microstates image shown here. We've made some nice enhancements to the ADMET modeler package for building predictive models. We've added 37 new modeling descriptors. That brings the total number, I believe, to around 410. The new descriptors are from several categories. This is all described in the user manual, and they include both 2D and 3D descriptors. The 3D descriptors require that the input compounds have 3D coordinates. We've extended the neural network modeling method to include a new option that we're calling linear boosting. So this involves adding a new layer of weights that directly connect the inputs with the single output. That's shown here with the red lines here. And the benefit of that is we found that it tends to mitigate a problem of output range compression. The next slide illustrates an example of that. So this is with just our default neural network method. Predicted values are shown on the x-axis here with observed values on the y. And you can see when we've observed this in several data sets where there's this artificial kind of truncation at both the low end and the high end, this sort of knife cut that you see here. And with the linear boosting option turned on, we find that it tends to greatly mitigate that problem. The user manual has a very nice write-up of how it works and why it works. So anyway, you'll see that as a new option when you build models using neural networks. For the time being, it is restricted to regression models, and we're going to look into whether it might be amenable to classification models as well. A few enhancements to the Medchem Designer sketch application. I'm just going to cover a couple of those. One is the ability to visualize transforms. So we have transforms both in the AIDD package that I've mentioned, as well as in metabolite generation. So now you can take a transform from either one of the files that we distribute with Predictor and just paste it into Medchem Designer and see a nice visualization of what that transform describes. And this also works just for arbitrary daylight smirks strings. You can paste those in to Designer and see a depiction of that transform. And then similarly, you can apply transforms within Medchem Designer now. So this works, for the types of transforms that we have in AIDD and metabolite generation, but there are also built-in transforms like tautomer standardization. So you can just sketch a compound in Designer and then use this transform feature and select tautomer standardization and see the resulting structure appear. We've been asked for this by a number of different clients. Just briefly, we've made kind of a small enhancement to the 3D virtual screening feature, and that is to allow disconnected fragments for the query. So the way this feature works, you use ADMET Predictor to construct a 3D conformer database, and then you can quickly search that database using a 3D, actually one or more 3D reference structures. It runs on the GPU, it's very fast. Prior to this release, you were restricted to a contiguous query structure. Now it works for a discontiguous one. So this is one where I'm actually searching it with just 5 disconnected atoms, and pharmacophore feature definitions have been applied to those atoms. So it's essentially a pharmacophore query. So we've just kind of expanded the utility of this existing feature within ADMET Predictor. And just to point out, all this 3D functionality is free with any paid property prediction license. So even if you just have the PCB module, you can use all of this 3D virtual screening functionality without obtaining any new license. And last but not least, we are introducing a new module called pyADMETPreictor that makes the AP12 command line and REST API accessible within the Python ecosystem. And I am not going to try to describe this further. I am instead going to hand things over to our in-house Python expert, Rafal Bachors. He designed this new Python module, and he is going to give a live demo of it for the next 20 minutes or so. Thank you, Rafal. I will hand it over to you if you can show your screen.
Sure. Thank you, David. Yep. So let me share the screen first. Okay. Can you confirm that you can see the Visual Studio Code?
Yeah, we can see it, Rafal. Yeah, looks good.
Yep, thank you. Yep, so good morning, good afternoon to everybody. So it's a great pleasure for me today to take you, for a short trip through pyADMETPreictor. As David mentioned, this is like a library interfacing ADMETPredictor capabilities with the Python ecosystem. So I'm going to show you a couple of use cases with pyADMETPredictor. All these files and the Jupyter notebook that you see right now, it will be delivered together with the AP12 distribution, so you can, install pyADMETPredictor and the other dependencies which are needed to launch this Jupyter notebook, and you can just do this exercise by yourself later on. Yeah, so here's the agenda on the left. So I have, as I mentioned, a couple of use cases involving ADMETPredictor capabilities like SMILE standardization, property calculation, pKa images generation, HTPK calculation, metabolite generation, and 3D geometry generation. I'm not sure if we will manage to go through all of them, but anyway, if not, then you can just do it by yourself later on. In the manual, you will find an in-detail information how to install the pyADMETPredictor. It is delivered as a wheel file together with the other files of ADMETPredictor 12, but we will publish that quickly on PyPI on this Python package index. So the installation is straightforward. You can just use the pip software to take it, from PyPI and install it into your local Python environment. So this is like a Visual Studio Code, the IDE I used to use. and we will be just going through and executing the code and, trying to find the synergy between, high quality ADMET Predictor capabilities and Python ecosystem. So first of all, I have it already prepared the environment. So I have pyADMET Predictor here. I have also ADMET Predictor service running. As David mentioned, pyADMET Predictor is capable of interfacing Python ecosystem to ADMET Predictor through command line and RESTful API. So first we have a couple of formal things like loading the helper functions that will help us a bit. And quickly we will start going through the use cases. So majority of the use cases rely on the small data set, the subset of WDI drug compounds. Natively, they are represented here as RDKit, a well-known Cheminformatics library object. This is, for example, the compound taken from this exemplary data set. This has been loaded from the SD file. And now the first case that we are going to go through is the SMILE standardization. So we will just take the SMILES in the raw form, and we will apply the SMILES cleaning standardization workflow, which is natively available in ADMET Predictor. It is mainly governed by this file. So we will be removing the common fragments, the smallest fragments. We'll be neutralizing acids and bases, standardizing the functional groups, and standardizing the tautomers. Yep, you have in the manual and also in this Jupyter notebook, you have the information that in order to get it running in your ecosystem, you have to slightly adjust the configuration files. This is restricted to providing the appropriate paths to the executable and this directory containing the input data. So after doing that, you can just launch the line or this bunch of code. And what is happening right now is we are exactly as it's depicted here. We are using command line interface to carry out this SMILE standardization calculation. Everything takes place in the temporary files area of the operating system. And as a response, we get the log content and the molecules. So normally when you do some batch calculations with ADMET Predictor, you get also the log file containing the information about the technical side of the calculation. Here you can find some information about potential problems, etc. So we can inspect that one. Everything went well here. And we get the Python list of RDKit molecule objects. These are exactly the resulting quantities. We were interested here in the SMILE standardization. So you can have a look here. This is the exemplary third or fourth element of that list containing the molecule. And here we have the parameters or attributes of this RDKit molecule objects. This is the SMILES code, the cleaned one here at the first position, and the raw SMILES, which were provided as the input information. So we can see that indeed the SMILES changed. So from this raw initial form, we ended up at this more correct standardized form. Yeah, so once we have it, we can take all these information from the list of molecules and represent it as a pandas data frame. And now, once we have it in that form, we can use the other entire zoo of capabilities of RDKit or Python ecosystem. For example, we can depict these molecules. Yeah, as an example, yeah, we can just try to find the pattern. This is again the part of the standard, portfolio functionalities of RDKit, finding the scaffold or the pattern, molecular pattern in the data. So just by using RDKit, we can just find, and select the molecules, the compounds which indeed contain that molecular motif. Once we have so now I'm switching to the next use case, which is the property calculation over the RESTful API. So once we have the smiles in a correct form, we can calculate the properties with ADMET Predictor. Here again, you have to make sure that the ADMET Predictor service is running and that you have properly configured the pyADMET Predictor. Simply, you have to provide the information about where this ADMET Predictor service is running, on which host and under which port. So here, I'm just starting that calculation. So we are providing the standardized smiles. Here you can see this list and the information about the property name under which the standardized smiles are provided. And here we've got, let's say, a call to ADMET Predictor service. This is the asynchronous call because it works in such a way that we simply throw in the calculation into the ADMET Predictor service. Then it is being processed, and ADMET Predictor service exposes another endpoint under which you can ping or ask for the results. And and here you don't have to worry about all these details because we have some helper functions that takes care of that. And here, after this asynchronous calls, you can just get these, calculated descriptors back, provided again as in the form of pandas data frame. Exactly the same can be carried out via command line interface. So the use cases from the business or user perspective, more or less the same. We provide the standardized smiles and we get back the properties, but simply we use a different technical mean to reach ADMET Predictor from the Python ecosystem. This time we are using command line wrapper, which is the interface to command line interface of ADMET Predictor. Again, we have a bunch of helper function which makes all these calculations, easy. We can inspect the log file created at the end of the calculation. And we can have a look at the molecules. This is a different molecule, and we can turn everything into the pandas database. And now, once we have this, high quality predictions from ADMET Predictor in the Python ecosystem, we can exploit the potential of Python. So here we've got the properties and descriptors, the PCB, physiochemical properties from ADMET Predictor and the descriptors. And our simple, as you can see here, we have them in the form of the pandas data frame. And our simple use case is illustrated here. This is a scikit-learn pipeline, computational pipeline involving standard scalar, principal component analysis, and stochastic neighbors embedding. And the key point here as an illustration is to take this 400 descriptors and properties, to scale it with a standard scalar, to reduce the dimensionality to 16 dimensions as an input to stochastic neighbor embeddings, which takes care of the rest. And at the end, we get a simple two-dimensional representation of our compounds, which can be easily depicted on the two-dimensional plane. And this is taking place right now. So we use a well-known scikit-learn interface, fit transform. And here on this data frame, we get this two-dimensional representation of our compounds, which we can use now for the visualization with matplotlib, which is another well-known library from Python ecosystem. So as you can see here, we have these two t-SNE components, as the direction of this two-dimensional plane, and of course the coordinates of these compounds or these dots or small circles, they represent the location of certain compound in the chemical space approximated by this embedding. Yeah, so going further, we can try to add a third dimension. So we have, let's say, the same distribution of the circles, but we add the color here, which is S log P property, which is obviously the octanol water partition coefficient. So yeah, this is a simple use case, you know, showing how you can find, you know, the best of these two, which is finding the synergy between the ADMET predictor properties and, broadly speaking, ADMET predictor capabilities and Python ecosystem. So now I'd like to switch to the next use case, which is PKA images generation. Again, we will be using the command line interface. As usually, you have to, if you want to repeat that calculation on your side, you have to have a look into this JSON configuration to adjust the paths to your local local environment, local file system. And again, we will be executing the ADMET Predictor workflow responsible for creating the PKA images. As before, so now, as you can see, we got three, let's say, objects as a result. This is a log content as before, the molecules as before, and the images. We can inspect the log content. So as you can see here, everything went well. Yep, and here you have the image of PKA microstates and macrostates together with the predictions of dissociation constants. So you can imagine now probably plenty of potential applications. So you can create a nice report, for example, involving your molecules. You can share that with your collaborators. You can present that to the other people. So I think there are a lot of things, a lot of benefits that might result from, you know, combining ADMET Predictor and Python ecosystem. So now again, I'm switching to the next use case, which is the HTPK calculation. As you know, ADMET Predictor offers the capability of calculating the PK properties. Here we'll be using RESTful API and we'll just provide the input structures and we will get back the PK properties in the form of CP time series. Yeah, these are some of the auxiliary function which can give you the information about the currently available PK properties. So this is one call, this is another call. And now we are just switching to the CP time curve predictions. I'm using the existing exemplary payload defining the HTPK calculation. So this calculation will be carried out for 3 compounds. Here we have the requested properties and some additional parameters. Of course, you can use the JSON module. You can, you know, take some sort of template of JSON payload. You can, here in the Python ecosystem, you can adjust it to your needs. You can modify that. You can do plenty of things in order to get the final payload you're going to use for your calculation. As before, we are just consuming the RESTful API of ADMET Predictor service, and we are getting back the results. And as the results, we have here the properties for all these 3 compounds, as well as the time series, the CP time curves in the serialized form. Of course, this is not suitable for I don't know, analysis or interpretation. We will be just deserializing that with Python. So here we can see 3 plots, 3 separate plots for these 3 compounds. But what we can do is we can, you know, take them and project onto the same time domain. Yeah, and here we can see the CP curves for these three compounds on the same time domain. Again, I'm switching to the next use case, which is, I think, almost the last one. This is the metabolite generation. As you know, ADMET Predictor is equipped with a very strong metabolite or metabolism module. And here we will be using command line interface to get the predicted metabolites of some input structures. As you can see, we have a repetitive motif. So all these pieces of code, they look almost the same, independent on the use case. Everything is included in the little configuration file, which just contains the information about the ADMET Predictor executable and the script which is going to be launched. And that's it. So here we are doing that again. So we are executing the code. Again, we get three returning quantities, which is log, content, the molecules, and the images. So we can have a look at the log content. Everything went well. Here we have the identifier. So all the metabolites and the mother or the native compounds that were provided as an input. And of course, we can just have a look at the exemplary metabolites. These are, as before, provided as RDKit objects. So we can use the RDKit capabilities to look at them. And of course, we can have a look at the ADMET Predictor native representation of that metabolism or metabolites picture, where we have the native compound and then the predicted metabolites together with the information about the enzymes involved in that metabolism routes. And this is now the very last use case, the 3D geometry generation. So as you know, ADMET Predictor is equipped with a very strong 3D capabilities. And what we will be doing now is we'll be just taking the 2D input structures expressed as smiles codes, and we will use the command line interface to get the 3D structures. Again, roughly the same, picture here, a piece of code that simply gives us an access to the ADMET Predictor command line interface. And you can use a very nice py3dmol module from Python ecosystem to visualize the molecule. And I think that's it. That was the last one. I'm hoping you will find it very useful. We are going to work on this. We are going to enhance this module. We would like to get some feedback from you. So if you would like to share with us any thoughts, if you like something here, or if you are missing some functionality, please let us know. We will do our best to fill up this gap. Thank you very much for your attention.
All right. Well, thank you, Rafał. Very nice work, and that turns ADMET Predictor in a pretty cool toolbox. So that's yeah, definitely pretty nifty stuff there. There was one question, I think, on metabolism, but that needed to be clarified, right, David? Did you obtain clarification on the question, or should we look for more?
I think we should. Unfortunately, I'm sharing now, so I'm not sure I can get back to Zoom. If you don't see anything in the panel, then I guess it was not clarified.
Okay. So, well, just a couple questions then on the release itself. When will it be actually available to download?
It is available. Yeah, as of
Okay.
this morning, the share file announcement should have gone out. So typically, I think there's maybe one or a couple individuals at each company that, get the email from ShareFile. These people have the authorization to download. So yeah, so both the Windows and the Linux version is available as of this morning.
Great. Thank you, David. Another question that often comes up is, are all users eligible to obtain new releases and updates. So I'll let you answer that one, but the answer is definitely yes, right?
Yes, absolutely. As you know, any releases that occur within the year, users with active licenses are entitled to
Yeah.
download those. Just in case it's something, I'm sure we've mentioned this before, but it's fine to have multiple installs of ADMET Predictor. So you can keep the ADMET Predictor 11 install and just install version 12 side by side.
That's right. That's right. You can have multiple versions of the software side by side that'll tap into the same license pool. So there's no issue in maintaining several versions together. So
Yep.
yeah.
And of course, yeah, the Windows and Linux versions can use the same license server as well, so you can install both.
Great, great. Yeah, you can run a Linux server at the same time that you using the software interactively. That we don't distinguish, like quote unquote batch licenses from the interactive use that uses the same license pool. All right. Well, if nothing else, let me look one last time into the Q&A pane. No, I don't see anything, so I'm just going to let Jasmine conclude our session, I think. Thank you to all of you for joining us today. I hope you found the presentations interesting. A big thank you to David and Rafael for sharing a lot of information with us today.
Yeah, thanks, Eric. Thank you, everyone. For any questions we were unable to answer or any that may come in, someone from our BD will follow up and answer those for you. You can reach out to us. We invite you to visit our website to learn more about ADMET Predictor. I put a link in the chat, and then you can also register for upcoming webinars. We have one for AI for pharmacological modeling on September 5th, and then another one for PBPK, PBPM, and support for BCS Class 3 waivers on September 24th. You can also follow us on social. I put a couple of those links in the chat. And then once again, this webinar has been recorded for playback and will be available on our website and YouTube channel. This concludes our webinar for today. Thank you, everyone.
All right.
Thank you.